Under Pressure 2, Direct and Inverse Relationships. Our learning targets are I can recognize a direct and inverse relationship on a graph, and I can write the mathematical equation for a direct and inverse relationship. What is pressure? In the picture below, you see that someone is pushing a tack into a block of wood with their thumb. The force on the thumb and the force that is being applied to the block are the same. However, the pressure that is exerted is different because the surface area of the head of the tack is much larger than the point of the tack. So therefore, the point of the tack will push through the board or the block there, but it will not pierce the person's thumb. So therefore, we understand that pressure equals a force divided by the area. Pressure is measured in kilopascals. The abbreviation is kPa. Standard air pressure is 101.3 kilopascals. Standard air pressure is just simply the air pressure in our atmosphere that we all experience every day on planet Earth. The effect of temperature on pressure. It's important to understand the definition of temperature. Temperature is the average kinetic energy of particles. If there is no energy, that means that there is no pressure. The temperature at which all particles stop moving is called absolute zero. Kelvin is the unit for this relative temperature scale. Absolute zero equals 0 K, and that is equal to negative 273 degrees Celsius. I can recognize a direct and inverse relationship on a graph. This first graph that you see here shows the relationship between temperature and pressure. This is called a direct relationship. In a direct relationship, pressure varies directly with temperature. We can see that on the graph that as the temperature increases as we move to the right, the pressure also increases. We can actually use an equation that represents this relationship, and that is right here, where the small k represents a constant number that is equal to the pressure divided by the temperature. This is called the gas law for pressure and temperature, or sometimes we call this Gay-Lussac's law. And this is the law that we investigated in the lab when we heated and cooled a flask of air to see how it affected the pressure of the gas inside the flask. The other type of relationship that we have investigated is an inverse relationship. In this case, the pressure varies inversely with volume. Another word for inversely that might be easier to understand is the word opposite. So as you can see here, as you increase your volume as you move right on the x-axis, your pressure is actually coming down. This is an inverse relationship. And the mathematical equation that represents this relationship is a constant number k, which equals P times V. This is called Boyle's law. And we investigated Boyle's law when we used the syringes that were full of air and place 10 milliliters of air in smaller or larger volumes to see how it affected the pressure. So now we're going to actually use those gas law equations in order to learn how to solve problems. So let's start with the inverse relationship. Once again, let's write down the equation that we can use to solve problems, where we have the constant number k, this is a constant, equals P times V. Now, if we wanted to solve for pressure here, we would have to manipulate this equation to solve for this variable. So, all we need to do is divide by V on each side, and we would have an equation to help us solve for pressure, where once again, this is a little k, which represents a constant number, and V, which is volume. Okay, so let's look at this in an example where we'll just use really easy numbers. So if we say volume is on the x-axis and pressure is on the y, we're going to set up our table like this, because we're going to change the volume to see how it affects the pressure. So volume is our independent variable and pressure is the dependent variable. So, and also the constant k has to be given to you. I would have to tell you what k is, or we would have to calculate it from data in a lab. So for the purpose of this little example, we're going to just say that k equals 2. All right? So let's say that we were going to start with a volume of 1. We can determine what the pressure would be at a volume of 1 milliliter if we said, okay, we're going to use this equation, k divided by V, so we'd have to take our k, divide it by the V, and we would get 2. So we can enter our pressure value there. Let's double the volume to see how that affects our pressure. So once again, we're going to say, okay, let's put in our numbers. K is still 2. Divide by 2 this time. And we get 1. So let's enter 1 for our pressure. And then let's double our volume again. So if we double the volume again, we'll put that into the equation where, once again, 2 is our K divided by the volume. And this time we get 1/2. Alright, so now let's look and see what has happened to our pressure each time that we doubled our volume. So when we went from 1 to 2, we multiplied our volume by 2. But notice what happened here. We went from 2 to 1. So we divided by 2. And then here, once again, from 2 to 4, we multiplied our volume by 2, and that resulted in our pressure cutting in half or dividing by 2. This is what happens in an inverse relationship. The volume in this case is doubled and the pressure is halved. Okay? Now, your K is not always going to be 2. Like I said, it would be given to you, but you would do the problems exactly the same way. So let's look at some data that looks familiar from our Boyle's Law lab. So let's write that up here. This was lab 1 from last week, and we were investigating Boyle's Law. All right. And so here's my question. What is the pressure when the volume in trial 1 is doubled? All right, so to answer that question, well, first of all, we have to look up here in our data table, and I didn't really label these trials, so I'll go ahead and do that now. All right, so we're talking about trial 1, which is right here, and the volume was 5.8. So this says, what is the pressure when the volume in trial 1 is doubled? Well, if we double the volume here, we can say, okay, well, 5.8, that's going to equal 11.6, right? So 11.6 would kind of go in here somewhere. That would be 5.8 times 2, right? So Let's do that. 5.8 times 2 equals 11.6 milliliters. So we want to find out what is the pressure at this volume. Well, you can solve this problem in two ways. The first way is just conceptually. Remember, we just learned that if you double your volume, what's going to happen to the pressure? Well, the pressure is going to be cut in half. So we can just go ahead and write that down. If volume is doubled, pressure is cut in half. So we could just simply look at the pressure at 5.8 and then cut this in half. So we would divide 175.9 by 2 to get that value. And so that would end up being about 88 kilopascals. All right? Okay, so that's the way we could think about this conceptually. But we can also check our answer. We can actually put this into the equation that we just used, where we can say pressure is equal to your K divided by the volume, to see if our math supports it. Because if the math supports what we just did here, we can feel pretty sure that we're right. So we're going to have to use a K. Now this time our K is 1025. And we actually calculated that in the lab. Yours might have been a little bit different. But it was around this number. Maybe you had 1030, maybe even 1050, and you may have even had a value that was not even 1000. But when you took the average, this is about what I got anyways. And then we want to divide that by the volume that we're looking for, the 11.6. And when you do that math, 1025 divided by 11.6, you get around 88 kilopascals. Now, it's not an accident that these two numbers are the same. Okay? Because this math just supports what we knew conceptually. All right, so on your worksheet, the lab analysis, now would be a good time to do that first page about Boyle's Law, since we just worked through an example. And when you're finished with that page, you can go ahead and come back and we'll start working on the direct relationship. All right, so now that we're going to look at a direct relationship, we're going to have to use a different equation. And so in this case, some constant number is equal to the pressure divided by the temperature. So in this case, K equals P divided by T. So if we want to solve for pressure in this type of problem, we would have to multiply both sides by T. So our T's would cancel over there. And our pressure is going to end up being equal to the temperature times the constant. All right. So now we're going to do another really simple example using easy numbers again. This time though, we're looking at the relationship between temperature and pressure instead of volume and pressure. So let's put our temperature here and our pressure here. And we're just going to use easy numbers again, and just for simplicity again as well, we're going to say that our K is 2. And we're going to use this equation to solve for pressure. Okay, so let's say that our temperature is 1 Kelvin. So in order to find out what our pressure is, we just use this equation where we take our temperature, which is 1, times the constant, which is 2. So our pressure is 2. All right. And then let's double our temperature. So now we have a temperature of 2 Kelvin. and we're going to multiply by the same constant there, and so we'll have a pressure of 4. And once again, these are all in kilopascals for pressure. And then we'll double our temperature again, and we'll do 4 times our constant and get 8. Okay, so let's take a look at our data and see what we can learn from this relationship. So when we went from 1 Kelvin to 2 Kelvin, we doubled our temperature. And when we did that, you can see that we also doubled the pressure. And then let's just see if that happened again. So when we doubled the temperature again, times 2, once again, the pressure was doubled. So this is a direct relationship, so that when you doubled the temperature, you also doubled the pressure. All right, let's look at an example from the lab, so some actual lab data. All right, so now we have some data, and this should look familiar. It should look a little bit like the data that we did in Lab 2, and this was the Gay-Lussac's law. All right, and we have our temperature in K here, and we have our pressure in kPa, and then this, the P divided by T, this is your constant for this set of data. Okay, so here's the question that I want you to consider. What would happen to the temperature if we doubled it? If we doubled the temperature, let's do this. Let's double the temperature in trial 3 here. Okay, so this is 1, this is 2, and this is 3. Okay, so what would happen if we doubled this temperature? Well, so let's write out the question. What would happen to pressure? What would the pressure be? Whoops, forgot the R there. The pressure be if the temperature in trial 3 were doubled. All right, so we can see that our temperature in trial 3 is 317.2. So if we doubled that temperature, and I'm doing the math right now as we're doing this, so we would end up with 634.5. So we can actually just go ahead and put this in our data table here. 634.5. All right. And so conceptually, what did we just learn about the relationship, in a direct relationship between temperature and pressure? Well, we learned that if we double the temperature, that will also double the pressure. So we could write that down. We could say when the temperature is doubled, the pressure is doubled. Okay? So that would mean that if that's the case, when temperature is doubled, the pressure is doubled, we would just have to take this number times 2. So we do 110.7 times 2. And we would get 221.4 kilopascals. All right, so now we can use our math to check that. So we could use our equation that we learned to calculate the pressure when you have a direct relationship. So we can say, okay, the pressure is going to be your constant times the temperature. Now for this set of data, your constant is here. It's 0.35. Okay? So we can say, all right, well, we would do pressure equals 0.35 times your temperature here, the 634.5. And I think we end up getting around 223, something like that. It's not exactly like it was in the chart. I'm going to double check this on my calculator. I was wrong. It's 222.1. So let me see if I can get my eraser out here, and we'll take that off. 222.1. That's even closer, so we'll take that. Okay, so, and this is pressure, so it's kPa. All right, now this is not exactly this number, but it's pretty close, so we'll take it. So I would say that yes, this supports our conceptual understanding that when your temperature is doubled, your pressure will double as well. Okay, so now at this point you should be able to do the work that's on the other side of the worksheet that's entitled Lab Analysis Lab 2. Okay, that concludes this video. Talk to you soon.